Now, next contributory talk is by Cupani Guido. He is from Osservatorio Astronomico di Trieste, so INF Trieste basically. He is a researcher at the Italian Institute of Astrophysics. He specialized in software solutions for medium to high resolution quasar spectrum. He has been part of VLT espresso spectrograph, and today he will be talking about advanced data analysis for observational cosmology, applications to the study of intergalactic medium. So now I request speaker to share his screen. Thank you.
The final goal of the present work is cosmology and fundamental physics. To this end, many investigations need luminous beacons at high redshift. If you want, for example, to determine the matter power spectrum at high redshift by measuring the fluctuations in the transmission of the intergalactic medium, you need bright beacon. If you want to measure the abundance of primordial elements, such as deuterium, to test the Big Bang nucleosynthesis, you need bright beacons. To put limits on the variation of fundamental constants, such as the phi structure constant or the electron-proton mass ratio, you need bright beacons. And to measure the variation of the expansion rate of the universe with the Sandwich test, you need the brightest possible quasars. Bright quasars and superstable spectrographs. Historically, in the southern hemisphere, where we Europeans have the best instruments and telescopes, such as Espresso and ESO VLT, there has been a dearth of luminous targets with respect to the north, due to the lack of appropriate surveys similar to the SLOA Digital Sky Survey. But time is ripe for a change thanks to new databases such as Gaia, WISE, SkyMapper, DES, and in the future LSST. However, quasars are rare objects, and high-redshift quasars are even rarer, so the problem is a classical search for needles in the haystack. And to save precious telescope time, since one night at ELT is expected to cost about 500 €, one needs the most advanced techniques tailored in terms of success rate and/or completeness. Afterwards, other advanced techniques will be required to analyze the high-resolution spectra of your quasars in the most reliable and repeatable way. Last but not the least, automated techniques allow us to apply the same procedure to data and to simulations, which is a must for the modern precision cosmology and fundamental physics.
The QUBRICS project aims to identify new, bright and high-redshift QSOs, or beacons, in the southern hemisphere. We used photometric data in publicly available surveys, analyzed by means of machine learning methods, in order to identify QSO candidates to be observed spectroscopically using facilities in the south. Finally, we use the acquired knowledge to address specific aspects of cosmology. The QUBRICS project already produced several published papers. A few more are currently under review, and more papers are yet to come. Note that the problem of finding high-redshift QSOs in the sky is actually twofold. We need to distinguish QSOs from stars, galaxies, and other sources in the first place, and then we need to estimate a redshift in order to discard low redshift candidates. The envisioned roadmap to tackle the problem is to create a database collecting photometric data and use it to train both classification and regression models, which eventually allowed us to identify QSO candidates. Here, we'll briefly describe the QUBRICS database. We collected data from the SkyMapper and the Pan-STAR surveys, and cross-matched against the WISE, Gaia, and 2MASS catalogs. The most relevant selection criteria are shown in this slide. The most important functionality provided by the database is that the final table collecting columns from the aforementioned catalogs is presented to the user as a live view, where each value can be traced back to the original catalog providing it. In other words, the link to the original catalog is always preserved, and we can switch from one catalog to the other as needed. A simplified version of the database is shown in this slide, where you can see the original catalogs on the left, feeding a number of standardized tables where, for instance, all magnitudes are given in the same photometric system, all object classifications use the same enumerated values, and so on. Each entry is identified by the name of the catalog and a specific source identifier. On the other end, we have the list of sources in the database, identified by a QUBRICS ID, or QID for short, and the table providing all possible match between the QIDs and the original identifiers on a specific catalog. These informations are joined together to produce a view with all columns from the different catalogs, and a row for each match. If a single QUBRICS source is matched in 2 or more catalogs, it will appear at least twice in this view. The final catalog to be used for training is generated starting from this view, but is filtered through a table specifying, for each QID and property, which catalog provides the most reliable value. The final view has now a single row for each QID, and the column report the best possible values for the source. By using the identifiers, we can reverse the whole process and trace back all entries to the original catalogs. Note that if a new and more reliable catalog is added, we simply need to update this table to switch to the new values.
The first QUBRICS selection was based on the canonical correlation analysis, that is essentially a higher dimensional selection process based on a linear combination of colors. And we applied this technique on photometric catalogs in the optical and infrared wavelength in order to select high-redshift QSO candidates. Since then, however, more advanced techniques have been applied to the QUBRICS selection, such as the probabilistic random forest and recently the XG boost. The probabilistic random forest is a generalization or modification of the original random forest, which is designed to properly handle measurement uncertainties. The idea underlying the implementation is to treat features, that is what we give as input to the algorithm, as a probability distribution function. This treatment improves the performances of the model and allows the probabilistic random forest to easily handle missing data. The XGBoost, instead, is a gradient boosting algorithm, and this means that the algorithm creates a model which is adjusted to accommodate misclassification, while at the same time controlling overfitting. Both of our models are trained to perform the selection in 2 stages. In the first step, we aim to select QSOs among other contaminants such as stars and galaxies that we instead wish to exclude. Once we have a sample of QSOs, we wish to remove low-redshift sources in order to select a sample of high-redshift QSO candidates. This second step, in particular, is not trivial. As you can see from the histogram on the slide, our training dataset is heavily skewed toward a low-redshift object, and this skewness degrades the performances of our selection algorithm. We found out, however, that oversampling technique were useful to recover some of the lost performances. As a final step, once we have a sample of high-redshift QSO candidates, we apply once again the XGBoost to estimate a redshift for each candidate. Finally, spectroscopic follow-up have been carried out in the past few months to confirm the nature of some of our candidates. And since the beginning of our survey, roughly 350 new high-redshift QSOs have been confirmed. You can see from the plot on the right the current state of the survey, where red dots represent new identification by QUBRICS, while black dots represent objects previously known from literature. As you can see from the pie chart below, after our runs, we found that low-redshift QSOs are the main contaminants for our survey, while we are able to reliably exclude stars and galaxies. In general, we find a good success rate, but there is obviously room for improvements. And we are currently testing synthetic data to avoid overfitting that can be caused by the skewed redshift distribution, and hopefully improve on the completeness side of the survey.
During the years, we have been putting together a number of workflows to analyze quasar spectra. That means to model their emission and absorption components and extract the information they contain. These workflows must not only be scientifically reliable, of course, but also durable. They must be designed and documented in a way that makes it easy to re-execute them, possibly across long periods of time. And we gradually realized that what we needed was not yet another software tool, but rather an environment to encapsulate all the workflows that we already had and construct new ones. Using a cooking metaphor, we needed a kitchen and a set of recipes, not just a pre-cooked meal. And this was the idea behind Astrocook, a Python package to design and run this kind of workflows in a controlled way. Here you can see Astrocook in action. Its most apparent feature is this graphical user interface, which allows for an immediate visual interaction with the data. The different recipes are accessed through the menus, and here, for example, you see an absorption system being first detected and then fitted with void profiles. Astrocook contains all our accumulated knowledge about the best ways to model this spectral component, first guessing the level of continuum, then identifying the lines, using the fitting line models to refine the continuum iteratively until we achieve convergence and we can validate it chi-square wise. But this is not all, actually. Astrocook comes with also a built-in login system that transforms these workflows into readable JSON files in real time. And this is both a documentation and a way to re-execute the workflows at a later time. Within the QUBRICS project, we used Astrocook in combination with another analysis software of ours, QSFit, to analyze a peculiar class of objects from the survey. And this is a good example of how these resources are actually used in practice. These objects are not immediately recognized as quasars from optical observations alone, so we decided to observe them in the near infrared to clarify their nature. We quadded the spectra, flux calibrated them, and corrected for reddening, and so on and so forth. And finally, many of them were identified as broad absorption line quasars, at redshifts around 2 or less, with a disproportionate fraction of quasars showing strong iron-2 absorption, the so-called fellow bulk quasars. These are strange objects, sometimes claimed to trace a transitional strong accretion phase in the evolution of aliens. We used the QSFit to estimate the mass of the black holes and add into ratios, and finally, we found no evidence about the evolutionary scenario for these objects. But anyway, the analysis is still ongoing. Notably, what we are about to do is to publish these results with a full runnable documentation of the procedure we adopted to foster further investigation. The bottom line is that in this era of big data, the most urgent scientific questions in cosmology and fundamental physics can be addressed only with a synergistic approach, combining several state-of-the-art software solutions. This means to cover also all the steps from data mining to data interpretation. And this is our effort and our challenge as we look forward to the next generation of extremely large telescopes.
Thanks a lot, Cupani and team. It was really a very nice journey through high-resolution spectroscopy of quasars. So now we have time of a couple of questions. And I can see one question by Shara on Discord channel. So it's like, so what do you do with the low Z contaminants that you are not interested in for QUBRICS?
Well, thank you. As a start, I would like also to thank the organizers for the possibility to give this talk. Actually, these low Z contaminants, for example, the one that we have shown, are very interesting for science. So we're not, of course, throwing them away. Also, we started the analysis of some of them. But since they are not our main interest, they will be, of course, included in the database, but with specific flags to recognize them. So sometimes also the serendipitous discoveries can be useful.
So let's thanks Cupani and team for this wonderful talk.